let's talk about how to make a 20-year-old single-player game into a multiplayer game. I've spent a lot of time the last couple of years modding an old PlayStation 2 game to make it multiplayer, and so this serves as an introduction into reverse engineering and how to use Ghidra, basically. So let's just jump into the fun part, which game this is. So this is Ratchet & Clank, a PlayStation 2 game, and this is from one of the early tests that I did with a friend when trying out this multiplayer stuff. You can see we're seeing each other and animations all work, and that's very cool. This is pretty early on. But okay, let's go over the agenda for this presentation. We'll start with getting started. This is like how do we find the code that we're looking for? How do we start getting reverse engineering started? And then we'll go over to making changes, like when we've reverse engineered stuff and we've found out how some parts of the code works. How do we actually make changes to the game and then load our own code? And then lastly, we'll just quickly go over how the multiplayer sort of works. Since this is an introduction to reverse engineering, the multiplayer part isn't that important. That's just regular networking code, if you can call any kind of networking code regular. But okay, we'll just start with getting started. How do we find our stuff? Well, we start out by assessing the target, right? So we need to know something about what are we reverse engineering. And first of all, Ratchet & Clank for the PlayStation 2 is a PlayStation 2 game, which means that it's running on the MIPS instruction set. We'll get more into the instruction sets if that's unfamiliar to you. The PlayStation 2 is severely memory constrained, especially these 3D games on the PlayStation 2. It only has, I think, 24 megs of RAM, so modding it is pretty difficult. And also, Ratchet & Clank relies heavily on dynamic code loading, which means that basically for Ratchet & Clank, almost every level in the game, or you could look at every level in the game as like a separate game binary. So every time you load a new planet, it's almost like you're just loading an entirely new binary. So this is one of those levels. Basically in Ghidra, what we've done when we want to reverse engineer one of the PlayStation 2 binaries is we take this, we take the whole memory currently loaded into the PlayStation 2 and just look at that. So we look at this raw binary executable, which kind of sucks. What you're seeing here is Orxon is one of the levels in the game, and then EE memory is Emotion Engine memory. It's just Emotion Engine is the processor. It's not important. The point is that this is just one level, and then you load that in, and then when you want to load a different level, everything changes. So if you have identify one function like memalloc, or malloc, which allocates memory, you can identify that in this level, and it will entirely change location for the next level. And there's no it's all ad hoc. So modding is it's annoying, to say the least. So luckily, Sony decided to have a port made for Ratchet & Clank for the PlayStation 3, which is great for us. Because PlayStation 3, well, the PowerPC doesn't really matter. The instruction set isn't that important, but it does run PowerPC. But the key part here is that the PlayStation 3 doesn't allow dynamic code, so you can't put new code into memory at runtime. Which means that this whole idea of unloading and loading everything, that's just gone, and now every single piece of code is loaded when the game starts, which is great. And also for modding, there's a lot of memory left now, because this is an old PlayStation 2 game. That just means that there's a bunch more memory as an overhead, just as a side effect of that. So also, this makes everything much easier. When we want to load this into Ghidra, this is just this is the binary. This eboot.elf, that is the only binary we ever need to care about. And this is just a regular old executable linking format file. Many of you may be familiar with this already. And so, Before we jump into all the nitty-gritty details of this, we will just have a look at what Ghidra is. What is this interface? Because if you're anything like me, you might have like tried to throw stuff into here before. You might even be familiar with stuff like Binary Ninja or Hopper or other types of like decompilers and disassemblers. And Ghidra looks more intimidating, I feel, in some ways, because for one, it looks like this old kind of Windows 95 app, but also there are like a whole bunch of windows, and there's a lot of information, and it's hard to know what's important. So let's just jump into the first thing, which is this this function symbol tree. So the symbol tree is where you have all the symbols. Like if you have functions and you have imports and exports. Basically, it's where you navigate to the different pieces of code within the application, and particularly the different pieces of code you already know about. And then we have the decompiler. So this is an approximation of the instructions in the binary. So instead, this is super helpful, because instead of looking at like a whole bunch of instructions where we don't know anything about like what's going on, and it's hard to assess the control flow of just like pieces of information or instructions, this is an approximation. So this is Ghidra's best attempt at taking all of the instructions and making it into readable code. As you can see, there's a bunch of like stuff here. This if true or true is kind of a weird thing. It's just a fault of the decompilation basically. But here you can see there's like a printf, and it says crap. And this is pretty funny. This is actually in the game. This is the start of the game loop for every level. So every time you load a level in the game, it starts by printing crap to the console, which is pretty funny. But yeah, there's the zero fill, right? There's load level files. Like all this is just like stuff that you can actually read and understand. And so we can continue on here. There's even more like planet loading, update hero, update Mobies. So this is debug update, debug update option. Very strange name. But this is readable, right? You can actually understand what's going on. Game state is planet loading. So you're starting to like understand that there's some actual stuff happening here. So the next important part is this define strings. It might not be in this tab. You might need to go to window and then find it somewhere. But this define strings is also super important, because this is where you like, if you have no symbols at all, if you have like everything is just unknown variables and stuff, this is where you kind of try to piece that info together. A lot of like these strings, it can be like your first path into trying to understand what's going on in some piece of code, which we'll look more into as well. So then there's this instruction set stuff, all these like the listing here. So this is the actual like data in the binary. This is the actual like, these are the instructions, and most importantly, this is the offset into the binary. Or sometimes you'll get like, if there's a Windows executable, these might be virtual addresses. But in our case, this matches exactly the address this code will be in RAM, and it also matches the offset into the file on disk. So that's pretty helpful. So this hex stuff, I don't think really needs to be there by default, but it is. But this is basically just the data that is at this specific point right now. So at this offset, you have this data, right? And then this last piece, these are the actual instructions. That's what this decodes to. So these are all, you can see these are all 4 bytes long, and that's because PowerPC is a fixed width instruction set. So they will always be 4 bytes basically. While Intel, for example, you will see these have varying lengths. But it isn't important. What is important is this piece, this code, that you almost never need to look at. If you need to like really understand, if something looks wrong in the decompilation, yes, look at this. But for the most part, you just look at the decomp, and that's more than fine. Okay, So let's start out now by looking at the PlayStation 3 executable files. By default, these come in like this eboot.bin, so they aren't named eboot.elf like I showed before, and that's because these are encrypted, basically. These are encrypted files that are also code signed, so they are distributed when game developers like distribute their binary. They send it to Sony, and Sony encrypts it and signs it, or I don't know the order of that. The important part is just that this is encrypted, and it is not an ELF in the first place. It's an SCE. So this magic header is just Sony Computer Entertainment, I think. It doesn't really matter. The point is it's encrypted. Now we can decrypt this pretty easily. We can just use RPCS3, which is a PS3 emulator if you're not familiar. And they, for whatever reason, they have a bunch of encryption keys in their source codes. They can just decrypt these binaries. I don't know the legality of that. That seems kind of risky, but here we are, and it's very helpful to us. That means we can get out this... click too far. Gotta wait for the animations. Thank you. So now we got this eboot.elf. We can see that it's not as encrypted as it was, or it's not as random as it was, which often means this isn't encrypted. We can now see that this is elf. The reason that there's a symbol before the elf is because this is a 64-bit elf, and the magic header for that has some byte in front, basically. Okay. So now, when we finally load our binary into Ghidra, we can see that Ghidra correctly identifies this as an executable in linking format, the ELF file, but it doesn't know the language. The language is blank because Ghidra doesn't actually have a disassembler for the specific instruction set that the PS3 uses. The PS3 uses a PowerPC 64-bit instruction set with 32-bit addressing. So it basically, because the PS3 only has 256 megabytes of RAM, it never needs to address more than 4 gigs of RAM, obviously. So they can have the system be 64-bit and handle a bunch of 64-bit stuff, but then have 32-bit addressing so that you save on some of that space. That saves a lot in the instruction space, basically. That means you can have 4 bytes of instructions or 4 32-bit instructions, but leaves you with 64 bits of calculation space or whatever. So in Ghidra, we use this PowerISA AltiVec 6432 adder. Basically what this means is the PowerPC, it's the PowerPC instruction set architecture with the AltiVec extension, and this matches almost what we need. This AltiVec extension is a vector extension, so that you can work more easily with vector instructions and do vector math. 64 is just because it's 64-bit and 32 adder. And so also of note is that this is big endian. Most instruction sets today use little endian, and so this is also sort of challenging. We'll get to that way later. So when we pick this language, we can finally start to analyze the eboot, and we just hit yes for this. And then for the most part, this is all, the standards are all fine. Like the defaults are all good, typically. So you don't, very often you don't have to worry about exactly what to put here. If you don't know what to put, you just hit analyze and that's all good. You don't need to like worry about much of the stuff that's in there unless you want to. But starting out, you just hit analyze and that's good. I know for this one that we should disable at least these two because they tend to be wrong and they're difficult to work with. And it just makes things difficult, really. So we uncheck those and hit analyze, and Ghidra starts working for a little while until we get to this interface. You might start somewhere else, but where I've started is I've looked at this defined strings, and we found this these common textures ret1% SCEA. So now we're in here. We've just analyzed this. There are no symbols Like nothing is named basically, and we can only figure out what things are based on the strings that we have here, or maybe we can like look at what a function does and try to figure out like what is this function. But it's much easier if you just get started with looking at the strings, just going somewhere and then start labeling stuff. So let's follow this cross-reference here that we saw, this cross-reference here, and see what the code is around here. So we'll see there's like a bunch of this like epilepsy warning, health warning, and then rat 1%. And this is likely this, right? When the game starts up, you'll get the health warning that's like, take 30 minutes break or whatever, blah, 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 right? And then you get this Sony computer chamber presents, and so that's probably this, right? So what we do is we start to rename, and renaming stuff, this is the most important part. You just need to rename stuff everywhere, really. But we rename this function, and I think we can rename this. This is probably like a splash screen. I don't know what you would call this. But what I typically do is, because I'm very bad at committing to things, I put these question marks at the beginning. Which like indicates, I don't know what this is. This might be wrong, right? And so you put all these question marks and then whatever you think you should name the function. And now we can see that there's like a whole bunch of like more useful stuff. All this is like play splash screen. So what happens now if you ever like go to somewhere like a whole totally different function and you see this like play splash screen and it doesn't match our first assumption, you just rename this to something else. Like if you get a hint from another place about what this could be, you just rename it. But at this point, you know that you've seen this function before, and you've made some sort of like you've had some idea of what this could be, and that really helps you later on, because like you'll see stuff that you start to recognize, and even if it's wrong, it's much easier to tell that you've seen this before, rather than going like, oh, I've seen this fun 1417 F0, right? That's it's impossible to remember that you've seen this before. So you just start to rename stuff. That's the most important part. So now, in Ratchet & Clank, there's this weapon called the Morph Array that it turns enemies into chickens, right? That's the purpose of this. So I thought a good place to try to figure out stuff is let's try to figure out where in the code this runs, right? And maybe we can change it to something else. So I think I know a lot about the game already. So I know that the way this works is that the weapon, it deletes the original enemy and it spawns a chicken in its place, basically. So what we can do is just let's try to find the spawn function. The spawn function should be one of the things that's it's one of the nicer things to find in the beginning, right? So we'll just go to these defined strings and maybe we'll look at something like spawn. I mean, there's nothing here that I think is super specifically in the spawn function. Some of this is related to spawning. Spawn something of something, right? And well, this must be a position, right? But yeah, what is of note in Ratchet specifically is there are these references to Mobies everywhere, and so that's just Insomniac, the developers of Ratchet & Clank. That's what they've named game objects, basically. So everything that's like a game object, they call a Moby. I don't know why that's a Moby. It's kind of cute, but it's strange. But let's look for this Moby stuff. And there are a whole bunch of references to Mobies, which is super nice. But this one is one of the more interesting in this case. Tried to create Moby and couldn't. And so we'll just click this, and you'll see we navigate to that in the listing, and then this is the reference. This is where this is used in the code. So if you can tell here, there's a whole bunch of references. So if something's used more times than just once, you'll see a list of references. But in this case, there's just this one reference, and we'll follow this reference now to where it's used in the code, and you can see this is used here. Tried to create Moby and couldn't. So this is probably a print statement, printf or something. It certainly does look like it. There's the %d and the %d. blah blah blah. So I mean, this doesn't really. Does this really tell us if this is a spawn function or not? I wouldn't really say that this is definitely a spawning function. But what we can do is we can go to the references of this one. So just like we saw before with the reference inline in the listing, we can find this in a new window like this. And so now we can just like go through this and like have a look at what's going on around this. And for example, we can stop here. Have a look at this one. So it's interesting to look at the parameter that's put in here. So if we go back now and look at this O class, right? So it tried to create a Moby and couldn't, and then said the time. So this is probably time, I guess. And then D. So this parameter here, this is probably the O class. And now, knowing knowing stuff about this game, and you can have a look in one of the level editors that is called Replanetizer by Milt Ratchet. And here are a bunch of like these Mobies, and they have all these like references. And so you can see like OX27A, that's this thing. So maybe this piece of code like spawns this thing. The hollow guys, that's is it called? I do know the name. It's okay. Let's just assume this is the spawn function and rename this to all question mark spawn Moby. I don't know. Maybe it's not spawn Moby. Who knows? Okay, so if we now try to find the morph-array chicken, so this chicken, we go to the level editor and we find the O class for the morph-array chicken. That's OX10E. And then we just we go through all the references and we just look. You can go through, like, there are 100 references probably to spawn Moby, but you have time. Like, you don't need an automated tool for this. You can just go through the list and try to find the parameters or look at how the function is called. So here we see this spawn Moby is called with OX10E. So this is probably where the chicken is. If this is the spawn Moby function, then we can try to change this into like the bolt crate instead, which is OX1F4, and see if that changes anything, right? So we can do that in Ghidra, and you can change stuff in Ghidra and then export this as a binary again, if you wanted to. That's not exactly how to do this with modding, but fuck. So we can change this in Ghidra. We can just like recompile this. We can use because Ghidra also works as an assembler in a simple capacity, and so we can like inline change this and change this from OX10E into 1F4. So you'll see this is like the new instruction that will encode to this old data, right? Okay, so we've changed this. Now it says spawn Moby 500. 500 is the decimal for 1F4, and should be the crate. So now let's have a look at what happens. All right, they changed into crates. This must be the spawn Moby function, right? Well, what else could it be? So this works now, and we can change them into taxis if we wanted to, or we can change them into parts of a train, which is not very helpful, but it does work. Okay, so now making changes. How do we get those changes into the game? Now that we've identified where stuff is, how do we actually get those changes into the game? So we have some challenges loading our codes. First of all, as I said in the intro, there's no dynamic code loading on the PlayStation 3. So that means that we can't just go into the process and say, hey, load this code for us. We need this to run at the runtime. And this is problematic even on emulator, because for RPCS3, one of the ways that it works is that they recompile the entire binary into Intel code or whatever platform you're on. and it's an optimization thing. So instead of like emulating everything, they kind of recompile it so that it runs much faster. And that's something that they've taken advantage of since almost no game. And I don't know if any game on the PlayStation 3 loads code dynamically at runtime. So they've taken advantage of that when making the emulator. Now, our other challenge is if we want this to actually run on the hardware, then we need some sort of code signing, which is partly solved by PlayStation 3 jailbreaks, but it's not fully. We won't get this to load on an unjailbroken PlayStation. So the code signing is luckily not a problem with emulator. We don't need to worry about that there. So this guy, TGE, he has created a wonderful framework for that solves a lot of this for us, which is called CKit. It replaces code in the original binary to make us be able to load an external library. But importantly, it also lets us hook functions in the game. And so it does like a lot of that stuff for us. It allows us to these external libraries. They're called PRX libraries on the PlayStation. They are basically like DLL files or SO files. Now, the CKit also re-implements parts of the C standard library because for whatever reason, when you load PRXs, you can't, or it's difficult to use the standard C library. I'm not really sure what's going on there. It's very annoying, but it's solvable, right? It's solvable, which is the most important part. But yeah, so we can load an external library, our own code, and we can hook and call game functions. So how does this work? We have the original executable, the eboot.elf, and so we need to kind of inject ourselves into there somehow. With the original eboot, there are a bunch of different ways we could do that. But one of the easiest ways is to just like extract parts of this eboot and put it into our own process. And now there's like a whole bunch of like available space for us to do our own things. And so what we do is we put our mod loading code, the code that actually loads our mod, this SPRX file. So when you start the game, this is loaded, this piece. So there's something missing, like there's some piece of code missing here. But this now allows us to load our own code, because in the entry point, like this is where, when you start the game, this is where the PlayStation like starts executing code, and somewhere very close there, we just jump over to our other piece of code here that is responsible for loading this whole like SPRX file, right? So whenever like the game actually needs to run this function that we've extracted, or this piece of code, like it jumps here, and then we just move it down to here, and so it just runs from there, and then when it's finished running there, it just jumps back to wherever it should have been in the original code. Now there's also a bunch of like memory hook code in here. Because we want to hook single like functions that are just one instruction long. Some are like, they're maybe like stub functions or some kind of trampoline functions that are only one instruction long. And if we want to hook them, we kind of need more. We need more space, and so that's what we have allocated for the rest of this that isn't just the mod loading code. So whenever like if we want to hook the rendering function or the on respawn function or any of these other functions, we have one instruction that jumps over to here, and then that jumps down into our like mod code. There are a whole bunch of details to this. It's a lot of like looking at assembly. It's annoying. But this is like sort of how it works. So now with CKit, we can use both C and C++. Although we have no support for exceptions, which is kind of sad. Exceptions are nice, but they're not necessary. We also have no standard library, which means we have to re-implement everything, including like memory allocation functions. So if you want to use malloc, you got to implement that yourself. And that's what I've done for Ratchet. So we can use C++, and it's almost, when you're writing like Ratchet multiplayer code for the mod, it's just like regular C++ in many ways, except there's no exceptions and parts of the standard library is missing. So that's just how it is. Okay. So now, if we want to like try to spawn something, let's have a goal where we spawn a crate above Ratchet's head that like follows Ratchet. I think that should be a manageable goal. That means we have to try to spawn an object and then move that object around in space. So I think we'll just like go back to our spawning function. This is where we spawn a Moby. And so that should be a good place to like start to understand. And what we need to find is where in this Moby is like structure. When we spawn a Moby, how do we change the position of the Moby? And so yet again, I think we can try to look at the references to this spawn Moby function and try to have a look at how when other functions spawn a Moby, how do they use that Moby, right? Because we return something here. We return this uvar, and whenever we can't create a Moby, it returns a 0 or a null pointer. So I think pretty clearly this returns the Moby that we just spawned. So how do they use it, right? We can have a look at this. This spawns some kind of Moby, right? We don't know. This spawns it based on the incoming parameter to this function. So we don't necessarily know what this is without following this function's references too. But what we can use, and what's nice is that if you see that it's used a lot, like when you see go through here, you can see that this ivar7, it's used a lot here for like ivar7 plus ox31 plus ox34 plus ox10, all this. And all that is like, that's a hint that this is a structure of some kind. It's not just an int. It's a pointer to somewhere in memory, and then all these like offsets are like offsets into that structure in memory. And so what we do is that we can auto create a structure with Ghidra, which is really nice. It's not perfect by any means, but it gives you a starting point to look at stuff, because all of these like OX blah blah blah, all the offsets are really hard to like parse mentally when you're looking at it. So what's nice to do is just auto create a structure right away, so that you have something to look at that's like a bit better, because now you can kind of tell what's here. This like becomes a struct. Ghidra just calls it a struct without asking for the name, which is kind of annoying. But now you can see that it looks like C and C++ like structure referencing, or I don't know what to call it, right? This is like usage of their fields, right? And that's much easier to have to look at and try to understand what's going on. It's not great. Ghidra also tries to infer what like the data types are. So it's like, oh, is this a short? Is this an int? Is it a 32-bit int? Is it a 64-bit int? All that stuff. So okay, looking at this, a struct is the name of this structure by default. Kind of sucks. So we rename that to Moby. You just double click it and open. And now you can see that there's like a whole bunch of fields here. So this is the offset, and by default it doesn't give you any names to any of it because it doesn't know. But now this size, I know for a fact that this size is wrong, but it will also probably almost, I mean, for the most part, it will be wrong, because it's hard to infer the size of these structures. And so what we need to figure out, or we don't have to figure out, but what it is nice to start to figure out what size this is. And we can go back to this spawn Moby function and try to like understand what's going on here. So this is a while loop. When it spawns, it's like a type of a linked list type of structure. But what's happening here is really that it's like it's starting in one end and then going through everything, it can be a bit hard to see here, but we have some hints here about what the size of this structure is, we rename this to Moby. This uvar3, it's nice to just rename that to Moby, so we can kind of tell what's going on. We're pretty sure that we're passing Mobies. You can see here it's plus ox20, plus OX120 and plus equals 100. So this is where it's interesting. This is what you should be looking at. This is a hint at what's going on. It's also kind of it's also trying to trick you in a way, but this is where it's at. So what's happening is we're going through Mobius, and then at the end of this, if we don't return something, clearly what we're doing is we're going to the next Moby in the list, right? So if there's a long list of Mobies, this is where it's like going to the next one. And so probably, I would say, Mobies are probably 256 bytes, or OX100 in hex, if you will. So now we put this OX100 and we edit the function signature. So this is also something you gotta do. You gotta edit these function signatures so that things are making more sense. And we say that it returns now a Moby, and it takes in a uint class. And then things are starting to look a bit better, I would say. So now you can see here, instead of this Moby plus equals 100, it says Moby plus 1, which is a classic way of like going to the next one in the list. Okay, so that's some of the Moby structure parsed. Now we know at least like how big it is, and it's a bit easier to understand what's going on. So if we want to figure out where does this go, I tried previously to like search for position and stuff, and I couldn't find something that was like clearly a position. But what we can try instead is to find this path. Like things follow paths all the time. So maybe like if a Moby follows a path, maybe we can try to like go into that. So this is like, okay, this class needs a rocket path. Rocket follows a path, right? Maybe we can like have a look at what's going on here. This is all a bunch of like jargon code. So first of all, we can see this param1. This is probably a Moby, right? Moby class %d. So plus OXA6 is the class, and then this instant %d is at offset b2. So this parameter, we go up like we did with the spawn Moby edit function signature. We edit this function signature so that this parameter, this param1, this the first argument passed into the function that we're looking at here, this fun 8038F55C, right? So this is the first parameter, and we can change that just like we changed this to a uint. We can change this parameter into a Moby, and then it starts to look like this: Moby field OXA6 and OXB2. So this is an undefined 2, and this is undefined 2. In Ghidra talk, this just means that it's a variable that Ghidra has identified as 2 bytes long, but it doesn't know like if it's a short or if it's an unsigned short, or maybe it's something else entirely. We can also have a look now at this, like these print statements. These I've already renamed this to printf because it's very clearly printf to me. And so this Moby class, now this field is probably called class, right? And this field is probably some kind of instance identifier maybe, but it does say instance, right? So we can change these. We can change in the structure editor, we go to A6 and change that into a ushort and name it class. And then we can change this into a ushort and name it instance. Now, I don't know for sure that this is a ushort or at all. Maybe it's a short instead, but it's not. I mean, it doesn't matter until it matters. Really. As long as things are looking fine, we can just accept it. But also, something else to note here is that this field says that it's a float, and it does something plus 20, and because often in processors, and particularly in the PlayStation 3 PowerPC's processor, floats use a different instruction than typical like integer instructions. So when you do math on them, it's you typically use a different like floating point instruction. And so when Ghidra says that this is a float, that it's doing like float stuff here, that probably means that this field is also a float. So So we can probably be pretty sure that this field that it's using, it's a float. And so we also changed this now into float. And so this piece of code will now look way easier to parse, right? Moby class, blah, blah, blah. And then this looks like normal code, right? This is just Moby class, Moby instance. And so there's a whole bunch of stuff like all around here that does not look like normal code. But at least this piece now looks like normal code. Sorry. And also now this part here just looks like some floating point stuff that is done. It no longer casts to a float because it is a float, so it doesn't need to cast. So okay, we've got some more info. We don't have what we're looking for, but this is a nice detour. It helps us along the way. So okay, I was looking for other stuff, other strings that maybe like are related to going somewhere, and I found this Moby wandered out of world. That's interesting, and it sets this field 18 to 3.0, and so that's interesting because it also does it to these other fields, and it does it. It sets 3 fields at the same time. So these are also probably floats. I know for a fact that 3.0 it encodes to 0x404, and so when we change those fields as well in the structure editor to being floats, it looks like this. 0x10 and 0x14, 0x18, they're all being set to 3.0. So that's still, I mean, that's certainly like, that reminds you of like a 3D position, the XYZ position, right? But it's not, I wouldn't say that like at this point you know that this is the position. But this is an interesting one. No final place for jet during victory, so use init pos. It certainly sounds like it's setting something, right? It's setting a position somewhere maybe. And so all these now are like, okay, param1, I made this into a Moby structure as well, into this incoming function in the parameter here. Or incoming parameter into this function rather. And so now these are being set in a row, right? And so maybe this function is related to this jet, and these are positions. I don't know what this 1c is. Maybe that's a state variable or something, or maybe it's a quaternion type of position. But we can start to try out stuff, right? We can change code, we can load our own code. So maybe it's time to just like try this out and see what happens. So let's write this code out. So for this structure, we just like make a mock structure for Moby, and so we don't know what the first like 16 bytes are in the Moby. So we just add a padding, and then we add float x, float y, and float z. And then we pad it out at the end. We don't really need to pad this out at the end, but it's nice if you want to. You can do this. So you don't need to know all the variables yet. You can just like start with a fleshed out structure, and then so I've done some magic here. I've hooked us into the on-game tick function in the game, and I've already found the Ratchet Moby. So we know where Ratchet is in the game. Oh, this is like this. I'm cheating. I am cheating. But we found the spawn Moby function together. So this is still relevant, right? And so we have this. We spawn this test Moby in the first tick. If it's not spawned yet, we just spawn this, right? And then since this runs every game tick, it runs 60 times per second. This should move the Moby above Ratchet's head. So we just put the Z position +2. This is in Ratchet and Clank. Z is a height, which is correct. Unity is wrong. Don't at me. And so this should now like it should spawn a crate, and it should move it above Ratchet's head every game tick. And so this will end up looking like this. There we go. A spawned vault crate that moves with Ratchet and is above his head and won't ever move unless you break it, I guess. Okay, so that's loading our code. That's making changes. We've figured stuff out, and we can make some actual like game. We do stuff to the game, right? Now we just need to make it multiplayer. Draw the rest of the owl. And so multiplayer, like I've done a lot of stuff. Like there's a directory to like choose the servers, and there are game modes where you're like, oh, this is tag, and so you can see each other. You can actually play like a game mode. And all that is handled by a server I've named Lawrence. Lawrence is a character in Ratchet 3, or introduced in Ratchet 3. He's a butler robot. I thought that's a fitting name for a server, isn't it? And so that's just the server code. I mean, that's not even modding at all. That's just writing code in C# that I've chosen to write it in C#. So all the core networking code is just C#. There's no like C++. There's no heavy code there that's like difficult. Well, I mean, my code might be difficult to parse, but it's not because you're like hacking some kind of binary. This is just a game server basically. And so the game modes, I've made an interface so that you can write game modes in Lua. I like Lua as a scripting language, which is why I chose that. It has like a really small runtime, and so it's nice to use. I need to charge my Mac because it's like almost dying. Yeah, it runs a custom UDP based protocol that I just made up basically, and I chose UDP over TCP because it's faster typically, and for the most part, like I send a lot of like updates about position, and none of those need like acknowledgement. And with TCP, that would kind of a lot of those are spammed, and they would kind of congest the traffic. So UDP is a better choice for this, and I like networking, so I don't mind dealing with the hassles of UDP. It is a hassle. The reason I have this includes basic RPC here is because this was difficult. Like UDP kind of sucks. And so it's nice to have some kind of basic RPC. There is some acknowledgement of packets. So if things are lost, the server should be handled. And I've also done testing so that to see that it's handled. It should be. Who knows? In practice, it's hard. So some of the networking challenges that I had is that the PlayStation 3 is big endian, which is super annoying. That's basically this thing, like, oh, you have this integer, and it's when you put it in memory, because you have like within 1 byte, within 8 bits, the order is the same in big endian and little endian, luckily, but it's the order in like where you place the next byte, because when you want to have like 32 bits to make 4 bytes, which order do you put those in? So you have this, let's say, have this OA, OB, OC, OD. Where do you put those? And the little endian, it's this order, and it's big endian, it's the opposite order. So PS3 is big endian, and most modern systems today, they're little endian, which is like all basically. I think ARM can be ARM, the mobile processor, can be big endian, but mostly today it is little endian. And all Intel is also little endian. So that's kind of annoying to deal with. There's also, since there are no libraries, since I can't use any libraries, I can't use OpenSSL. This is really bugging me. As someone who works in security, and I think everything that's made today should just be encrypted. This irks me so much. That I can't use like OpenSSL, or I can't use any like library to just wrap my protocol up to have encryption. I also can't do HTTP. Like there are no like simple libraries to just do HTTP. I would have to write that myself. So that's also, everything has to be done through that silly UDP protocol, which is also super. It would be nice to be able to do some stuff over HTTP, because then I could do like authentication or other stuff, especially if I could have HTTPS. But that's not happening right now, at least. So yeah, wrapping up, I would say that the essence of multiplayer mods, like when it all comes down to like what do you need to get this working in the first place? Like, what's the minimal thing you need? And it's these things. It's these two things, and then this is basically everything else, right? But it's spawning game objects. You need a way to like spawn game objects, because otherwise, how do you see what's going on, right? And then you need to have a way to move those game objects. And then everything else, like if you can do those two things, everything else is just like a bunch of code. And if you already know how to write code, writing code is never easy, right? It's always buggy, and it's always a lot of troubleshooting. It's always like a bunch of shit, right? But when you know how to do those things, you can do everything else, just like Googling and checking out things on the web, right? And then other interactions, they're just flavor. They're just extra stuff, right? Of course it's nice to like understanding how weapons work, like when someone shoots at you, how do you react to that? If someone like hits you, how do you do collisions? All that is obviously nice stuff to have, and ultimately that makes for a better multiplayer mod. But these two things, these are the essence. This is what makes it, and when you have that, you can have everything else. So okay, here are some of the code contributors to the multiplayer mods. Panatis is helping a lot. Does his username has always been helpful. Fusion Lore also has done some stuff. So I wanted to recognize these people. There's nothing is done just by yourself. You need help from people. There's also a bunch of reverse engineering contributors. These people have done helpful work to reverse engineer the binary. It hasn't been worked only by me. I would say a bunch of these people have done way better and more work than I have. Yeah, that's Chaotic Milch Ratchet. Does his username in Isak. Super great people. Thank you a lot for doing all this work. Yeah, reverse engineering is a lot of fun. You should really get into it, and you'll find all these like funny strings and shit that developers have put into their binaries. So I hope that's been a helpful sort of introduction into Ghidra reverse engineering, or at least like a look at how this can be done. Like, it's not, you need to start somewhere, right? And so thank you.